Perfect. So this is our set of notes on electrolytic cells. So now an electrolytic cell is a cell. Let me just see what's going on here. Let me make sure I've got my pen ready. And is used to cause a chemical change through applied chemical energy from a battery. So this requires an outside energy source. So it uses electrical energy, right? So this is an outside energy source to make a non-spontaneous redox reaction to occur, right? Oxidation and reduction. So now our voltaic, I'm just going to jot that down on here. Our voltaic was spontaneous. And it gives chemical energy to electrical energy, right? That's our energy conversion, electrical. And so now our electrolytic is where we have an outside energy source, so it's not spontaneous. And then now instead of chemical to electrical, it's reversed electrical, because this is, if we're starting with a battery, we're starting with electrical energy. So electrical to chemical. And this is a non-spontaneous oxidation and reduction, right? We have a battery that forces the reaction to go through. So in this case, because we're connecting something to a battery, remember batteries have positive and negative ends, that our anode in this case is positive, which is the opposite of a voltaic. So this is one of the changes in the differences between electrolytic and voltaic. And our cathode in this case is negative. And our cathode is at the negative end of the battery. So the negative battery is where our cathode is, right? Because that's the negative end of our battery, because the electrons still flow from anode to cathode. And remember, the electricity is the flow of electrons, and the battery forces the direction of the electron flow. There's no salt bridge in an electrolytic cell, right? Because we have that battery, so we don't need to have that balance of charges that we have from the voltaic. So one type of electrolytic cell is electrolysis. Notice how they all have the same prefix, electro, right? So it has to do with electrons, and we need electricity. So this is where electricity is used to force a non-spontaneous chemical reaction. So it's an electrolytic cell. And electroplating is a very good example of electrolysis. So electroplating is when you take a cheap metal, and then you basically coat that metal with a more expensive metal. So basically like pennies with the copper, they don't dip pennies, which are mostly made up of zinc. They don't dip them in molten vats of copper. It's done by electroplating. And this is an example down here at the bottom of electroplating. So we have an electrical current that causes the more expensive metal in electroplating, copper, silver, gold usually, to attach to a less expensive metal. So these are like kind of how like fake gold watches, how you can make like silver spoons and whatnot. So here's an example. Let me see if I move this over here, down here. Let me move that over here. So this is an example of electroplating. So I know that this is going to be an electrolytic. Let me make sure I've got my pen here. So this is going to be electrolytic. So I'm not sure why my pen doesn't want to seem to work here. Why doesn't my pen want to work here? Oh, I don't want to do that. I don't know. So it's this here. Okay. All right, so this is electrolytic. Electroplating is electrolytic. It requires a battery. So this is non-spontaneous. Right? And so it's going to take this electrical energy and convert it to electrical energy. And what we're going to do is we're going to be putting a different metal, silver, on top of this key. So now electrons always go from the anode to the cathode, right, and through the wire. So in this case, then we have the electron is going to flow out of the negative end of the battery, right? And so here our cathode is going to get bigger, because if I'm electroplating this key, right, that means that it's going to have a even build up all the way around of metal on top of that key. So we always say the fat red cat. In this case, our cathode is negative because it is attached to our negative end of the battery, right? And then our electrons go from here. This is our anode, right? And then here's our anode, which is going to get smaller, right? Because it's going to still lose electrons. And then as it loses electrons, it's going to end up dissolving in the aqueous solution, which is our silver ions. And then those silver ions gain the electrons from over here, and then they end up attaching all over as a very thin coating on our key, which is going to be our cathode. And so again, anode is going to be the higher metal on table J. So generally, in this case, you have the anode is this bar, and then our cathode is going to be the key because we don't know what the metal is. And that wraps up the differences between the electrolytic cell and the voltaic cell. So again, the most important thing here, right? We still have electrons going from our anode to the cathode through the wire. There's no salt bridge. Right here we have, and oops, I made it to go backwards. And here we still have in an aqueous solution, we still need an electrolyte. So maybe this would be maybe silver nitrate, for example. So you might see AgNO3AQ, right? Because remember then we have our silver ions, and our silver ions go out here through there. All right, so this is how we can do this thing with gold as well. We can electroplate silver, gold, copper. Generally, that's what an electrolytic cell is. So then also for electrolysis, we can also split sodium chloride, right? And we can split that into sodium and chlorine ions through electrolysis. Right, we can also do electrolysis of water, right? And we can split water into our H plus and our OH minus. So then these require electricity and outside energy source. We can still write half reactions. So this wraps up the redox set of notes, and keep watching and go back and rewind if you need some further clarification.